Today we're going to be talking about exponential functions. We're going to start first with our vocab. Exponential growth is just an increase in quantity whose rate of change grows more rapidly over time, while exponential decay is a decrease in quantity whose rate of change decays more rapidly over time. And last, we have a horizontal asymptote, which is a horizontal line that the graph is going to get closer and closer to. It's going to approach, but it's never actually going to cross it. So now I'm going to take a quick minute to compare the three types of functions that we have learned about this year. I'm going to start with my linear functions. If you remember, a linear function, when it's in its basic form, is going to have an equation of y equals x. So for its table, y equals x, remember I can make a table from that by putting that in my calculator and hitting second graph. Now, I always want to use the x values of -2, -1, 0, 1, and 2. And that is true for both linear and exponential functions. It will not be true for quadratic because remember, quadratic, we have to start with the vertex. All right, so think about this. This is saying y is the same value as x. So if x is -2, y has to be -2. If x is -1, y is -1. If x is 0, y is 0. If x is 1, y is 1. And if x is 2, y is 2. Now I'm just going to plot those points on my graph. Don't forget, I'm going to connect those and add arrows to both sides. So remember, a linear function should always form a straight line. Now for quadratic functions, its most basic form is y equals x squared. I am not going to always be able to use -2 through +2 because it all is based off of the vertex. We always want to put the vertex in the middle and pick 2 to the left and 2 to the right. Now, if I type in y equals x squared to my calculator and I look at the graph, the vertex is actually at 0, 0. And I know that because it's sandwiched between the values of 1. So I have also a value at -2, +4, and +2, +4. I'm going to plot those points on my graph. And remember, a quadratic function should take the shape of a U or a parabola. Do the best you can in drawing that. It's okay if it's not perfect. Add your arrows to each end. Now for exponential, the most basic form is going to be 2 to the power of x. So I know that an equation is representing an exponential relationship because x is in the exponent. So again, I'm going to use my x values of -2, -1, 0, 1, and 2. I can just type that equation in my graphing calculator, hit second graph, and copy down the table or the y values that are associated with those. I can also take that and plug it in for my x value. So that gives me a value of 1/4, 1/2, 1, 2, and 4. And I'm going to do my best to plot those points because I do have some fractions. So that's about 1/4, about 1/2, 1, 2, and 4. This is going to be in the shape of an L. Again, do the best you can and add arrows. It's okay if it's not perfect. So when we look at these three different functions, based off the equation, if I have an x as the highest exponent, then that's always a linear function. It's going to be a straight line on my graph. If I see an x squared as my highest exponent, that's always going to be a quadratic function that takes the shape of a U, which is a parabola. If I have x in my exponent, that's going to be exponential, and it's going to take the shape of an L or a backwards L. So for the rest of this lesson, we're going to focus strictly on our exponential functions. We're going to start first by graphing the same way that we've been graphing each time we've learned about new functions. We are simply going to type that equation into my graphing calculator, and we are going to copy down our table. For exponential functions, again, we're going to continue to use our x values of -2, -1, 0, 1, and 2. So if I type this in the y equals screen of my calculator and I hit second graph, I am going to get my table. So at -2, you might see the fraction 1/9, or that's the same thing as 0.1 repeating. At -1, we see 1/3, which remember is the same thing as 0.3 repeating. You can put either one. I don't mind which one of those fraction or decimal that you use. At 0, we have a value of 1. At 1, we have a value of 3. And at x is 2, we have a value at 9. We are going to take those and plot these on our graph. Obviously, the fractions are the most challenging to graph. Just do the best you can. 1/9 is going to be really close to that x-axis, but it's slightly above. 1/3 is about right here. 0, 1. We have 1, 3. And our 2, 9 is really far off my graph, so I'm going to just stop there. And I'm going to connect all of my points. Again, do the best you can. It's okay if it's not perfect. Add arrows. Now we're going to identify our key features. Most of these we have seen before. The only new ones are horizontal asymptote and whether or not it shows growth or decay. I'm going to start first with my x-intercept. My x-intercept is where it crosses the x-axis. Well, in order to understand this, I'm going to talk about that horizontal asymptote. Remember in my vocab, a horizontal asymptote is a horizontal line that my graph is approaching but will never actually cross. So that would be an example right here. You can see that my graph is getting closer and closer and closer to that x-axis, but it's never actually going to cross. It's going to stay just barely above it, and that's because each time it's going to microscopically move down. So that horizontal asymptote is at the value of my x-axis. Well, since it's a horizontal line, remember it has to be in the equation of y equals, and this is a y value at 0. So my x-intercept, because it's never going to actually hit when y is 0, there actually isn't an x-intercept. So we're just going to say none or an A. For my y-intercept, that is going to be, again, where it crosses that y-axis. So I can see that on the graph, or I could even see it on my table, because remember, it is when x is 0. So that is an ordered pair at 0, 1. For domain, my graph is going to continue moving left and right, so that means my domain must be all real numbers. It doesn't stop. And lastly, my range. My range, you can see, appears above that horizontal asymptote, so that means all my y values have to be bigger than 0. It's not going to be equal 0 because remember, it's never actually going to hit that horizontal asymptote. So it's just the values above 0. Now the last key feature is if it's growth or decay. Now think about it, you read a book from left to right. So if I start on the left side of my graph and I move to the right, you can see my graph is going up. You can also tell by looking at my table, as I move up on my x values, my y values also get bigger. They move in the same direction. That is an example of exponential growth. All right, so let's look at another problem. I'm going to go into my graphing calculator. I'm going to type my given equation. I'm going to come up with my table. Remember, I'm always using the x values of -2, -1, 0, 1, and 2. If I copy my table down, I have 4, 2, 1, 1/2, or it might say 0.5, and 1/4, or it might say 0.25. Now I'm going to plot those points. So I have -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. Again, do the best you can, connecting all of these values. You should see that L shape take place. Add arrows. Now we're going to identify our key features. I'm going to basically start first with that horizontal asymptote. I can see that it's again approaching our x-axis. It's where it's kind of leveling out, bottoming out. So that's going to give me a horizontal asymptote again at y equals 0. Now that doesn't mean that that is always the case. It's the most common, but that doesn't mean that's the only situation we see. Now that I know my horizontal asymptote, I'm going to look at my x-intercept. Remember, it's never going to actually touch that x-axis, so there isn't an x-intercept. For my y-intercept, remember, it is where it crosses the y-axis, or again on the table, it's where x is 0. So that is an ordered pair at 0, 1. Next is my domain and range. Again, this graph is continuing to the left forever and to the right forever, so that makes the domain all real numbers. And my range, again, you can see my graph is above that horizontal asymptote, so that means my y values have to all be greater than 0. Now, again, it will not be equal to because it will never actually hit that x-axis. Lastly, I'm going to look for if it's growth or decay. Again, if I read from left to right, you can see my graph is going down. That is an example of decay. If you look at your table, you can see that as my x values are getting bigger, my y values are actually getting smaller. They're moving in opposite directions. That will always be a dead giveaway that it's an example of decay. Now, really quickly, to fully understand our asymptotes, I'm going to give you a couple more examples just so you can fully get what I mean by the asymptote. So if I have a graph that looks like this, and let's say I have a exponential function that looks like that. That horizontal asymptote is actually flattening out right here. And I'm going to write a horizontal equation for that. Remember, horizontal equations are y equals, and it's flattening out at the y value of 2. So my horizontal asymptote is at y equals 2. Let me give you one more, again, to help you fully understand what's happening here. If I have a graph that looks, let's say that this graph is right about like this, then that would create a horizontal asymptote right where it's kind of flattening out. And that would be at a y value of 4. So my horizontal asymptote would be y equals 4. In that case, my range would have to be anything bigger than 4. So that would be y is greater than 4. Your range is built off of your horizontal asymptote. All right, now that we've talked about graphing exponential functions, we're going to look at some word problems for growth and decay. First, I'm going to kind of compare growth and decay. I'm going to start first with my growth. Remember, this is a graph that is rising over time, so I'm just going to draw a rough sketch of that. Decay would be an example of going down over time. Now, when dealing with exponential equations, we actually have two different formulas that we use. The first I'm going to talk about is y equals a times b to the x power. So we first need to talk about what are the pieces of this equation so that we can understand. In this case, the a value is always going to be my starting value, or I can think about it as my y-intercept. My b value is always going to be my rate of change. This is really important that we understand that rate of change is written in words. So for example, I might say when talking about growth, I might use words like twice or double. When talking about decay, I might say things like half or a third. So whenever I see that my rate of change is given in words like twice, double, half, a third, I'm going to be using this equation y equals a times b to the x. What I'm going to do is just plug in the values that I'm given. I'm going to type it in my calculator and get a numerical value. I'm going to look at these two problems. The first says bunnies can double every month if we start with only 3 bunnies. Since this says that it doubles every month, then that is an automatic giveaway that it's getting bigger, which is an example of growth. How many bunnies will we have by the end of 7 months? So I'm going to start first with my equation, which is y equals a times b to the x. I know I'm using this equation because it has the word double. I'm going to plug in what I know. Y stays y every time. A is my starting amount. I start with 3 bunnies, so that's going to go in for A. And B is my rate of change. My rate of change is that I'm doubling. If you double, that is an example of 2. My exponent is going to stay x. Now, it's really important to understand that this exponent is measured in whatever units that my rate of change is happening. So my rate of change is doubling every month. So that means my x is measured in months. So what I'm going to do is I'm going to go into my calculator. I'm going to type in my equation, y equals 3 times 2 to the x power. And then I'm going to look at our table, and I'm going to look for when x is 7, because I'm asking about how much will we have in 7 months. And since x is measured in months, I'm looking for the x value to be 7. If I look at that table, I get the value of 384 bunnies. Another option is you could take the equation of y equals 3 times 2 to the x and change the x to be a 7 for 7 months. I can go into my home screen of my graphing calculator and I could type in just this part of my equation, and it would also give me the answer 384. Now remember, we talked about the fact that this is an example of growth, so make sure that your answer makes sense. If I started with 3 bunnies and I'm up to 384 bunnies, that shows that it is getting bigger, so I know I've done it correctly. All right, now let's look at another example. This time it's going to be a decay problem. It says each year the country club has a tennis tournament that starts with 128 players. During each round, half of the players are eliminated. How many players remain after 5 rounds? Now I know this is an example of decay because I see the word half, and because I see that the rate of change is in a word format, I know I'm going to use the equation y equals a times b to the x. I'm going to plug in what I know. Remember, the a is the starting value. I'm going to start with 128 players, so that goes in for a. B is my rate of change. Half is my rate of change, so that's 1/2. You can also use 0.5, and that says each round half are eliminated. So x is actually representing the number of rounds. We want to know how many players remain after 5 rounds. So again, I could go into my calculator, type this into y equals, and I'm looking for x to be 5. When I do that, I will see that that would leave me 4 players after 5 rounds. Again, if you wanted, you could also just type in my home screen of my calculator, 128 times 1/2 raised to the 5th power for the 5 rounds. You will still ultimately come up with the same answer, that y is equal to 4 players. All right, so now we need to talk about what happens if the word problem doesn't give us our rate of change in a word format. We're instead going to use this equation, y equals a times 1 plus r raised to the t power, or it could also be 1 minus r raised to the t power. This sign in the middle all depends on if I'm talking about growth or if I'm talking about decay. Now I use this equation whenever my r value is in the form of a percent. So in this equation, our a is still our starting value, or you can think your y-intercept. R is going to be your rate of growth or decay, depending upon which one you have. This is going to be a percent that we have to write as a decimal. Has to be in decimal form. And then t is always going to represent our time. Now the same is true if we're talking about growth. We're still going to have a as our starting value or our y-intercept. Our r this time is going to be our rate of decay. Again, it's always going to be a percent that is written as a decimal. And T is always going to be our time. So let's look at two word problems that have to do with this. We have a certain type of bacteria grows at a rate of 3% each day. So there's a couple of important pieces here. It grows, so that tells me growth. That tells me I'm going to be adding, and it grows at a rate of 3% each day. Since I see a percent sign, that automatically tells me I'm going to be using my equation that has an R in it. And I'm going to be using a plus because it's growing. So that's the format we're going to use. And remember, since it says 3% each day, we know that our time is being measured in days. Now I'm going to go ahead and look at my equation. I'm going to plug in what I know. It says if a biologist starts with a sample of 50 spores, so remember that's my starting value, so that's my A. It's always going to be a 1 right here. And then my rate is 3%. But remember, I can't put a percentage in my equation. I have to make it a decimal. So to do that, I move it twice to the left, and that becomes 0.03. Now I can leave that T technically as an X in my calculator. If I did that, remember I could then just go to my table and I can look when X is 30, or my other option is I can just plug a 30 in for my exponent, and then I can type that in my home screen, and that's going to tell me that I have 121 spores. Now, a couple things I need to point out right here that are super important is that one, this right here is symbolizing 100% plus an additional 3% each day. So it's 100% of the original value from the day before plus an additional 3%. That's why the 1 is there. 100% in decimal form would be 1 whole. The next thing I need to point out is the fact that I wrote it as 121 spores and I did not have a decimal answer. You are going to have to interpret these results and understand when you need to round and when you need to drop the decimal altogether. In this case, we can't have a decimal of a spore. We either have a whole spore or we don't. And so we dropped the entire decimal and we just left it at 121. All right, let's look at the next example. It says a tropic fish species has begun to decrease. There's my giveaway that it's decay, which tells me I'm going to subtract in population by 2.5% each year. Remember, when I see a percent, that automatically tells me I'm going to be using my equation that has an R in it. And since it's decreasing, I know it's going to be 1 minus R. It says if there are 500,000 fish currently, how many will there be in 4 years? So I'm going to plug in what I know. My starting amount is 500,000 fish. Remember, it's always going to be 1, which represents 100% of the fish from the day before, minus my rate, 2.5%. Yes, it has a decimal in it, but it's not in decimal form. So I still have to move it twice to the left. So I get 0.025. Again, I can leave this as an X, or I can go ahead and plug in my time. I know my time is measured in years because that's what my rate of change says. So it says how many will there be in 4 years? So I'm going to put a 4 in for my exponent. Now think about this. This is asking how many fish there will be. I cannot have half a fish. I either have a fish or I don't. So that's a dead giveaway that I'm going to have to drop my decimal. So when I type this in the calculator, I'm going to get that I have 451,843 fish. I never will round up on these. I will always just cut the decimal off because I won't have had time for it to reach the next fish fully. All right, we have a couple more examples. The population of a city has shown decline in recent years. That tells me it's decreasing, it's decay. When a city monitor counted the number of residents, he counted 89,051. He knows the rate of decline is around 4%. Percent tells me which equation I'm going to use. Every 3 years. How many residents can the city monitor expect after 9 years? So which equation setup are we going to use? We are going to use the one with an R. And since it's decline, we are going to make sure we subtract that R. Now we're going to write the equation that represents this problem. I'm going to plug in what I know. I know I'm starting with a value of 89,051. I'm going to have 1 minus my rate. Now my rate is 4%, so remember I have to change it to a decimal. That becomes 0.04. Now here's the hard part. My exponent in this case is talking about years. It says it right here, but it's every 3 years. So that's super important because that means it's not happening every single year. It's happening 1 out of 3. And I'm going to leave my t as time. All right, so now part C says, what does the t value in this equation represent? And this is the number of years. I know that because it tells me it's 4% every 3 years. That is the unit of measure. D says, how many residents will there be after 9 years? So I'm going to take that equation I wrote on part B, and this time I'm going to replace that exponent, the t value, with 9. So I'm still going to have 1 out of 3 years, and that has to be multiplied by 9. So if you think about it, if I have 9 years and it's happening 1 out of every 3, that's only going to happen a total of 3 times. You could go ahead and multiply this together to get that that is the same thing as 3. Again, I'm going to type that in my calculator. Since I'm talking about residents, which are people, I drop my decimal and I can only have whole values. That should give you 78,786 residents. And it should make sense because we said that it's declining, it's going down, that I have fewer residents than what I started with. All right, let's look at example number 2. It says data suggests a new product is tripling in value every 2 years. If the original value of the product is $4.50, how much will the product be worth in 8 years? So my rate of change is tripling, and since it's a word, it tells me I'm going to be using my equation that has a B. Now we're going to write the equation that represents this problem. I'm going to start first with my starting value, which I start with $4.50. times my rate of change, which is tripling. So that would be a 3 every 2 years. Years is going to be my unit of measure. And since it happens every 2, it's happening 1 out of 2 years. And we don't know how many years, so I'm going to leave that as an X. All right, part C says, what does the X value in this equation represent? This is still representing the number of years. Part D says, how much will the product be worth in 8 years? So what I'm going to do is I'm going to replace that X with an 8, still leaving the fraction of 1/2. And it's 1/2 times 4. So I could go ahead and simplify this 1/2 times 4. Well, half of 4 is the same thing as 2. And this is what I can type in my calculator. Since I am talking about money, I'm going to have to go to the hundreds place. And remember, I'm never going to round up. I'm just going to drop my decimal so that it would be $364.50. Part E is super important because a lot of people struggle with this. It says, what does the A and B represent in the equation and what is the value? So you should have 2 answers. What does it represent and value? Well, for A represents this original value, and the value was $4.50. B represents the rate of change, which remember is tripling. So that would be a value of 3. Just so you understand, you are going to use the represent would be the original value or the rate of change tripling. And the value is actually a numerical number. All right, last problem, number 3. It says, if the population of a pride of lions is observed to be 23 and their population is declining by 0.5% each year, after how many years will the pride no longer exist? So on this one, I'm going to be using my equation with the r, and since it's declining, I know I'm going to be subtracting r. I'm going to plug in what I know. I know I'm starting with 23 lions, so that's my A value. I know it's decreasing at 0.5%, but remember that's not in percent form. I still have to move it 2 to the left. So that's actually going to be 0.005. And my time is going to be each year. That is what it's measured in. All right, now my calculator is not going to let me type in a t, so what you could technically do is you could change that to be an x. So you can go into your calculator and type in y equals 23, 1 minus 0.005 raised to the x power in the y equals screen. Then what I'm going to do is I'm going to hit second graph, and I'm looking for when y drops below 1, because once it drops below 1, there is no longer a full lion left. That may take some time scrolling. You could also hit second window and change what your x value starts at. This might take you some time because you might have to guess and check. Guess how many years and then check to see if that's correct or not. If you do this one correctly, at year 626, it will drop below 1 lion, which would technically consider that all lions are extinct.